Hello everyone, welcome back to this algorithm with Python series, and in this video we are going to implement BFS algorithm using Python. So before we dive right into programming itself, we will discuss the graph that we saw in the previous video, just to remember the things that we discussed, and then we will implement them right on in our VS Code using Python programming. So the left hand side is the graph that we discussed in the previous video. A is the source node here, and B and D are its neighbors, and C is the neighbor of B, and E and F are the neighbors of D, and similarly G and H are the neighbors of E and F. What we have here is a graph, and we have implemented that graph using Python here. So I've just created it, before recording this video, just to save a little bit of time. So here you can see we have this A node and its neighbors are B and D. And you can verify that this is our node A and its neighbors are B and D. Next, we have node B and its neighbors are A and C. So this is node B and its neighbors are A and C. And similarly, we have a node C and its neighbor is only B. And here we have this node C and its neighbor is only B. And next comes D and its neighbors are A, E, and F. So here we have this node D and its neighbors are A, E, and F. And similarly, for all the nodes, we have their neighbors stored in them in the form of dictionary. So this is the adjacent list dictionary, and in that dictionary we have stored the nodes and their neighbors as keys and values. So let's just go ahead, and I will maximize this window so we can work on our code. So we will simply just go ahead and uh, write the algorithm for DFS code. So for the moment, I will just remove this terminal because we don't need it, and we will just go ahead and write code. So in this video, we will actually implement our BFS, and there are three other things that we will find using that BFS algorithm. The first one is finding the traversal order in BFS. So what it actually means is we will find that how using a BFS, how our algorithm actually moves in this graph. I mean, in which direction it goes first and in which direction it goes second, and how it moves between nodes, right? The second is the shortest distance between node and the source node. For example, if I talk about the node G, so what is the shortest distance between G and A? We will find that. And the third part is we will actually print out the path between a certain node and a source node. So in this case, we will take A as a source node, just like in the previous video, we selected A for our source node, right? So first of all, what I will do, I will initiate the dictionaries, and then I will give them the initial values. Let's just dive right into this video and see what I'm actually saying that. So what we discussed in the previous video is that we need to keep the track of all the visited nodes, right? So for that, I will create a visited dictionary, and in this dictionary I will store all the nodes that we have already visited. Then will come the level. So level, in other words, is just a distance of a certain node from the source node, right? So for that, I will also initiate a dictionary, and then comes the parent. So parent is the parent node of a certain node. For example, if I just go here, here I have this A, and this is a source node, which means this is the first node, so it has no parent, right? But when we go to node D, then its parent node is A, right? So these are the parent nodes. So we also have to keep a record of this. So this will also be another dictionary. Now what we want is we want to store the traversal order, right? This is the first part of the question. So we will let's say we will say BFS traversal order. So it will be a list that will contain the path or the order in which our BFS algorithm will move from one node to another, right from the source to the last node in the graph. Then we also discussed in the previous video that we need queue. So queue is a data structure that will help us in order to implement a BFS, because we need this data structure to add the certain node and then remove that node from the queue, just to add its neighbors in the queue. So in order to implement BFS, we need this queue data structure, and we can initiate it using this function. And remember, I have imported this queue from queue in Python. So these are the, we have initiated all the, we have, defined these entities that we are going to need in this code. Now we will give them their initial values. So for that, let's just say our source node is A, right? In this example, we are taking A as a source node. If that's the case, then we will initiate level and visited dictionary using this source node. So we will say that our in our visited dictionary, we have our source node. So for that, we will just go ahead and give a true flag to it. So it says that this source node, which has A, it is present in our visit dictionary. And how we are saying that? We are just giving it a true flag. We also have to define the level or the distance of A from source node, which in this case is A itself. So the distance is going to be 0. So we will say level for source node, obviously, and it's going to be 0 because source node is also A. And next comes our queue, right? So first of all, what we will do, we will initiate our queue, and we will initiate it using our source node, which in this case is A. So our queue will have A. I will just go ahead and write in the comment queue as A. Now first, when I will pop this A, then its neighbors will be added into this queue, right? So for example, the neighbors of A are B and D. So when I will pop this A, when I will remove this A from this queue, then its neighbors are going to be added into this queue, which are B and C. So that's what we discussed in the previous video, right? In the theoretical part of this BFS algorithm. So that's we have to do in the coming code, right? So let's just start the loop, which will traverse through the entire graph. But first, we have to, give the initial values. We still have to, uh, we still have to define our initial values to the graph. So let's just go here, and here we can see for node. So this is the for node in, because this is the graph that we defined. So we are obviously we're going to look for node in this adjacent graph, right? So we will say adjacent list, and the node will be in the keys, obviously, right? Because the neighbors are stored in the values, so the keys will give us the nodes, right? So if that's the case, then first of all we have to give the initial values to these dictionaries, right? And after that we will define all this. So first of all, our visited, for each node, our visited is going to be 0, obviously, because right now we didn't start to traverse in the graph, right? So in that case, our visited dictionary should be false for each node, right? And the level, because we did not traverse through the graph yet, so the level, we don't have the value of level, so we will also give it a value of none or -1. And the parent, because for the same reason as these two entities, the parent will also be none, because we don't have any kind of value, we have not traversed in the graph itself. So we will simply just go ahead and we will say that for each node in visited, we don't know anything, so this node is not present in the visit dictionary, so it's going to be false. And the same will be done with level. and you can say -1, and the same will be done with parent. uh, no node is going to have a parent node because we have not traversed into this graph yet. So these are the initial values of all the dictionaries for all the nodes, and then what we have done is we have defined that, okay, before we didn't traverse in the graph, right, but now we want to. So we have defined, or we have started a graph or all the dictionaries. So the source node will be A, and when we will start traversing, so first of all we will go to A. So this A is going to be present in visited, right? So we gave it a flag true, and then the level of A from A is 0, so we gave it a value, and then we added that into our queue, right? So at this point we have A here. So in the next steps, what we will do, we will just pop this, and its neighbors will be added to this queue, right? So let's see just how all of this happens. And while adding all those elements into the queue, we will also get the values for our BFS traversal order and visited and level and parent. So let's just go ahead and see how it's done. So first of all, we have to start a loop, and we will start it when our queue is not null. So we have a source node in it, right? So we'll say while queue is not none. We can say, or we can also say while not queue empty. If that's the case, then first of all, what you want to do is you want to pop whatever present in that queue. In this case, it's A. So we will just go ahead and call our queue, and from that queue we will get the first element, right? So it's gonna be A, and in this case it's gonna be A. Otherwise, this get takes the very first value present in the queue, right? The very first value that was added into the queue. So whatever that value will be, we will store that value into U. Let's just take U as a variable. And what we want to do is, because we want to keep track of all the nodes, and we want to see that from which node to which node we are moving, we will store this node to the order of the traversal, right? uh, right here. So what we will do is we will simply call our BFS traversal order, and we will append this U into this list, just to keep a record of all the nodes that we will traverse to. For example, in this case is A. If in the next iteration it will be B or G or H or whatever, all of that will be added into this list. Okay, so after doing that, what we want is, okay, we pop this A, and after popping this A, what we want to do is add its neighbor into this queue, right? So first of all, we will see what are its neighbors. So for V in, uh, I would say, adjacent list of U. So we will see in the dictionary what is stored against this U that we just popped from our queue, which in this case is A. So obviously, in the case of A, its neighbors will be B and D, right? So in the first citation, it can be B, and in the next citation, it can be D. So first of all, just check that if they're present in visited, and if not, if the visited of V is not present, then what you have to do is you have to add it to the visited, right? So the way we do it is simply give it a true flag, right? In the next iteration, what you want to do is you want to uh, take it and add it into the parent. I mean, oh, you can, what you have to do is you have to give its parents information, right? So in this case is we will say that parent of V is U, obviously, because V is the neighbor of U, right? So the neighbor from which we are moving to this V, from to this V node, uh, that neighbor is actually its parent, right? In this case, if we just go here, So from A to D, let's say we were moving to D. This V, the V we are talking about, let's say this V is this D, right? So we went from A to D, right? So A in this case is U and D is in this case V. So this U is the parent of D, right? So that's what we are saying, that parent of V or parent of D node is A node, right? So we are storing this value into this parent dictionary, right? Against this V node. So after doing that, we have to calculate the level as well. So the way we do it, we will say the level of V is equal to the level of previous node, which is level of U plus 1. Right? So in the first iteration, the level of U will be 0. So when we will move from A to D, so 0 plus 1, it will be 1. In the next iteration, it will be 1 plus 1 and 2. Right? So when we will go to G, then it will be 2 plus 1 equal to 3. So that's how this level will increase. So after doing that, what we have to do is we have to put that neighbor into the queue, right? Remember? So for that, we can do is we can call our queue and we can put our v neighbor inside that queue. And the next iteration, it will be done again. We will you know pop that v, and then we will add that v into this order list, and then we will check that if its neighbors are present in the visited. If not, then we will add them into the visited, and then we will give parent dictionary the value of its parents, and then we will calculate the level for this new neighbor, and then we will add this new node or new neighbor into this queue again, and it will go on again and again until our graph ends. So I think that should be it for this algorithm. So if we just go ahead and print the BFS traversal order, you can simply just save this program, and we will run this program using Python. And okay, so here you can see how our graph is actually moving from source to the last of the node. So first of all, it starts from A, then it goes to B and D, which means that B and D are the direct neighbors of A. Then comes C, E, and F. So C, E, and F, they are neighbors of B and D. And then comes G and H, which are neighbors of C, E, and F. We will just go ahead and verify this. Here you can see B and D are the neighbors of A. So you can see after A, B and D comes. C, E, and F, they are neighbors of B and D. So C, E, and F, they come after B, D. And then comes G and H because they are neighbors of E and F, right? So that's how our BFS algorithm traverses in the graph. Okay, so that's the first part of the question because we wanted to find the traversal order in the BFS, right? So what if we want to find the shortest distance of a node from the source? How can we find that? So first of all, we have to know that we were storing the distance or the level value into this level dictionary, right? So we can simply use that dictionary to find the value. First of all, let's just go ahead and print the entire level dictionary, and it will give us the levels for the distances of all the nodes from A. So here you can see the level of A is 0 because the distance from A to A itself, it's 0. B is 1 because B is the direct neighbor of A. I will again go ahead and open up that image so we can verify all the information. So here we have this image, right? Okay. So A is level of A is 0 because that's itself okay. So A itself, its level is 0 because it's a source node, right? But when we go to B, so B is a direct neighbor of A, right? So its level should be 1. And here you can see its level is 1. And then comes C. So C is the neighbor of B, right? So if we talk about A, then it's 2 steps away from A, right? First, you will have to go to B from A, and then from B, you will go to C. So 1 plus 1, 2. So its level is 2. When we'll talk about D, D is a direct neighbor of A, so its level will be 1. When we'll talk about E, then exactly like C, it's for E the level is 2, because from A to D the level will be 1, and from D to E it will be 1. So 1 plus 1, the level will be 2. And same we will go to F. So the level of level of F from A, it's 2, because A to D 1 and D to F again 1. So 1 plus 1, it will be 2. Then we will talk about G. So first of all, you will go from A to D, it's one level, D to E, it's second level, and E to G, it's third level. So 1 plus 1 plus 1, it will be 3. And same goes for H. It will be A to D1, D to F1, and F to H1. So 1 plus 1 plus 1, it will be 3. So remember, we are talking about the shortest distances, right? I mean, we could also go from A, D, E, G, and H, but that's the longest part, or the longest path, right? We are actually talking about the shortest path here. So in that case, we will take A, D, F, and H, and the level will be 3. Okay, so what if I mean, we have verified all these values and these values are correct, but what if I wanted to find the value of a specific node? What if I wanted to find the level of a specific node? So for example, if I wanted to find the level of G node, so I will just write G here, and here you can see it's telling me that the level of G is 3. Okay, so the second part of the problem is also solved. Now, the third part is print out the path itself of a specific node from source. Right. So for that, I will just simply go ahead and comment this out, and we will create a list in which we will store the path that we want to print out. Right. And here we will take a node. I mean, let's take G here as well. So we want to find the path from A to G. So we can say that while V is not none, obviously, if we will have this V, only then we can find the distance or the path, right? If that's true, then what you can do is call your path and append that V in it, and in the next iteration call your parent, because the parent dictionary had all the information of your parent nodes, right? So if I want to find the path from G, so what I actually can do is I can connect its parent nodes, right? This is G right here. Okay, so if I want to find its path from A, all I have to do is I have to keep the record of its parents that are stored in the parent dictionary. So first of all, its G's parent is E, and E's parent is D, and D's parent is A, and that information is stored in parent dictionary. So for that reason, I will simply call my parent dictionary, and from parent dictionary I will give this V. So basically what I'm doing is I am asking this dictionary to give me all the values saved against this V, and I will store this into V variable itself. So I think that should be enough. What we have to do is we have to reverse this path list, right? Because if we don't, if I just go ahead and print my path right now, it will give me the path from G to A. But actually, we want to find the path from A, which is source, to G. So if I just run this program, and you can see it's giving me G, E, D, A. But that's the reverse order. We want it from source to the node, right? So all we have to do is, because path is the list, we can simply call our reverse function, and we can save this program and run it again, and here we have the entire path from source node A to a specific node G. For example, if you want to find the path to, let's say H. You will just go ahead and save this program and run it again. And this is the path from A to H. Let's verify this. So here is our A node. This is a source node. Then, and we want to go to H, right? And we have to take the shortest path. So first of all, we will go from A to D. Then we will go to F from D, and then we will go to H from F. So A, D, F, and H, and that's what our program has printed. So that's how you can implement your BFS algorithm using Python in VS Code.